Okay.
So, hello everyone. We have Ratul Mahanta again for his final lecture. And yeah, over to Ratul.
Okay. So today I will discuss Dirac field and its quantization. So I will mostly follow Peskin and Schroeder, and I have added in the reference list a new book. So I will follow that. So it's by Amitabh Lahiri and P.B. Pal. So I recall that during my first course, I consulted this book and I thought that it might be an easier option or like a straightforward approach for a first course in quantum field theory. So although I will be following the fourth chapter, but for my lecture, you can look at the first four chapters. Yeah. Okay. So I will introduce Dirac equations. So we have seen that the relativistic energy momentum relation is this. And in a sense, today we'll evaluate this square root. So for that, we need to introduce some matrices. And whenever so this is a number, and these are the momentum number, and this gamma are the matrices. They are a set of matrices. In general, I will denote it by gamma mu as gamma 0, gamma 3. And repeated indices are summed over. But this side also there is a matrix because E is a number. So why matrices are needed? Because we are essentially doing the square root. And we will see now that if we square it, we will get E squared times identity. And in this side, we will get which will eventually we will get gamma 0, gamma j. Okay, so this quantity we would like to equate with p square plus m square times identity. Okay, so this should be the case. So immediately we know what properties these gamma matrices should have. For example, this gamma 0 square, it should be identity. You can also write it down about the linear term. It should be vanishing because pi are the arbitrary momenta and they are numbers. So these are the matrices which should be vanishing, and gamma 0 square is identity. So what will we get? Gamma is minus gamma 0, gamma I, gamma 0. And also from the first term square in momenta, it should be proportional to delta ij. But since these numbers, product of numbers are symmetric, pi times pj, so only the symmetric part will be restricted because the antisymmetric part, if there is any antisymmetric part, it will automatically go away. So it is the symmetric part on which you have to put a restriction. But yeah, so it is gamma 0, gamma j, gamma 0, gamma I equals to 2 delta ij. and times identity. I will not write this identity many often, just assume they are because these gammas are matrices, and these can be arranged by multiplying by gamma 0 in a suitable form, or you can use this relation, and this can be arranged in this form. Also, this relation can be, okay, so yeah, so this relation can be arranged. The first one can be arranged in delta ij, and this relation can be arranged as gamma I, gamma 0. Okay, so you can combine this thing in a single relation, which is gamma 0, gamma mu equals to 2 eta mu nu times identity. So this should be the final relation that combines all the formulas written above. Okay, so I should state some properties. For example, gamma 0 square is identity. Similarly, this will lead to gamma I square is minus identity. And you can also compute the traces from here. And you will see that all the gamma matrices are traceless. And these properties are already encoded in the relation which I have written in box. Okay, so let us check one trace by maybe using this relation. Yeah. So we know that gamma I is minus gamma 0, gamma I, gamma 0. And trace of gamma I would be minus trace of gamma 0, gamma I, gamma 0. And trace of AB is trace of BA. So immediately you can write this, and this is identity. So it is nothing but trace of gamma I, which implies trace of gamma I equals to 0 for I equals to 1, 2, 3. So you can also prove the trace of gamma 0 to be 0. Okay. I should add more property, which is not encoded in this boxed relation. By the way, I think okay, at this stage, I will also define an anti-commutator between gamma mu, gamma nu. So unlike the commutator, it between matrices, it comes with a plus in between the terms. So this notation I will always sometimes use. Okay, so we also want the operator. This should be the Hamiltonian. This operator on the right hand side in the energy relation to be an Hermitian operator, and this will lead to certain relations. For any momentum, we need it to be operators, and momentum are so far just real numbers. So you can take an Hermitian conjugate and see the final results will be this. So these are added property. Okay, so gamma 0 is Hermitian, gamma I is not. You can also combine it in a nice fashion in this way. Okay, so the derivations are given in my notes, so you can look at there. Okay, now you can see that from the relations, gamma 0 square is identity and gamma I square is minus identity. You know that the eigenvalues of these are because determinant of gamma 0 square is identity and determinant of each gamma I square is -1. And you can, and the eigenvalues should, determinant should be product of eigenvalues. From there, you know that it could be ±1. Yeah. Determinant of gamma 0 is ±1. On the other hand, determinant of gamma I is ±I. So this should be there, and the eigenvalues are ±1 and ±I. On the other hand, you know that the trace is summed over eigenvalues, and from there you know that gamma matrices should have even dimensional representation. So these are even dimensional matrices because the eigenvalues are always comes with some number and its opposite sign, and the trace is 0. So better be the number of positive eigenvalues equals to number of negative eigenvalues. Okay, so gamma mu are even dimensional matrices. In 4 spacetime dimensions, yeah. So in 4 spacetime dimensions, we need 4 anti-commuting gamma matrices, right? They anti-commutes. You can see from relations like these. Whenever you set mu not equals to nu, so whenever mu not equals to nu, this relation should equals to 0, and they are anti-commuting rather than commuting. So for example, from the relation you can find that gamma I, gamma 0 is minus gamma 0, gamma I. So these are the anti-commutations. So in 4 spacetime dimensions, we need 4 anti-commuting matrices, gamma mu, which is not possible for 2 by 2 matrices, not possible for 2 by 2 matrices. Because there are, you know that one candidate could be Pauli matrices, but they are only 3. On the other hand, then the lowest dimensional representation above 2 is 4 by 4. And there are solutions, and will not specify until the very end of the lecture what are these gamma matrices, because representation will not matter. Whatever discussion I will be mostly dealing with. So for our case, they are 4 by 4 matrices, each of them. Okay. However, in lower space-time dimensions, for example, 2 or 3, you can have 2 by 2 gamma matrices. Now, the usual rule that substitute these to get an wave equation. I am so far talking about a wave equation, and you can see from the relation E psi this leads to the Dirac equation. So what is Dirac equation? It is gamma 0, del 0. Del 0 is del t. Del I is del xi. So in we can write it in some fashion. Okay, so I should write del 0 is del t and del I is del del xi. But these are multiplied by some 4 by 4 matrices. So psi has 4 components. It is also a column matrix. Okay. So it turns out that if you want to compute the square root of the energy momentum relation, the wave functions can be only multi-component. But we will not go to the wave function interpretation. We'll because it will lead to negative energy states. But we will try to construct a classical field theory whose field equation, the Euler-Lagrange equation, will be this Dirac equation. So before going to that, I should write it in more compact form. So this is the Dirac equation. People also write this del slash notation. So which means it is defined as gamma mu del x mu. And also many often will use p slash for the momentum, or so it is usually defined in similar way that yeah. Okay, so now this is the Dirac equation. We'll try to find a field theory whose Euler-Lagrange equation is this Dirac equation. Okay, so before going to that, I should introduce. Well, it's not mandatory, but I will introduce some special variables which are anti-commuting variables, which will be called Grassmann variables. So in the canonical quantizations, it is not necessary. And that's what most of the books, even the 2 books I have referred, use that. But I will be introducing Grassmann variables. It is because it's tailor-made to deal with anti-commuting operators, anti-commuting fields. And for path integral quantizations, it is actually necessary. You will see later. And this will lead to basically Pauli exclusion principle. Although we can by hand attend, could have introduced some anti-commutator, but to begin with, I will be using these variables. So what are they? So we will treat, we'll see that, okay, so they are 4 by 4 matrices. So alpha are the alpha-th component of alpha runs over 1, 2, 3, 4. And we have to introduce 2 fields because these are complex. So its complex conjugate will also be used. Although this bar notation is not really complex conjugate, but I will discuss. So far, consider that you have 2 set of variables, alpha, beta both run over these because they are matrix elements, and there will be some derivatives in the field in the Lagrangian. So these are the quantity that will enter in the Lagrangian. We will write an Lagrangian soon. But this quantity will be complex Grassmann variables. Okay, so what are Grassmann variables? So I should define. Okay. So suppose you have a set of Grassmann variables. They should satisfy some properties, that is the anti-commuting. They will anti-commute, which will immediately imply that phi I square will be 0, because phi I plus again equals to 0, which implies phi I square equals to 0. So you cannot have any square of a Grassmann variable. And they can be some function of x. So we are just treating the fields as itself belong to this set of variables. And how do you write a function of this variable? Function of this variable is always will be in a polynomial, and this can be written as C0. Okay, so they are totally antisymmetric complex number. So they are usual complex number. Usual complex numbers, and totally antisymmetric. I will explain this in an example. Say n equals to 1 case. A function, there is only one variable. A function will be nothing but a complex number times another complex number times the Grassmann variables. Grassmann variable. N equals to 2, you have two Grassmann variable, call it theta 1 and theta 2. It will be C0, C1 theta 1 plus C2 theta 2 plus some number theta 1 theta 2. So you can see that theta 1 square, theta 2 square, even any higher order terms are not possible. Only square terms can come when they are distinct. Otherwise, they will anti-commute and make it to 0. So these are typical functions of Grassmann variables. They are in single variable, they are always linear. You can see that there is no phi 1 square terms or phi 2 square term. I just discussed it. And also for differentiation, since they are anti-commuting, whenever you are differentiating, for example, say you are differentiating with respect to theta 2, you have to bring theta 2 on the left and then take derivative. So the third property is on differentiation. So that would be, say, it C2 will contribute and minus C12. Theta 1, because you have to first write it as minus C12 theta 2 theta 1 and then take a derivative. So whatever the variable you are differentiating with, in the expression you have to first shift it towards left and then take a derivative. Or another way you can think of, because both are Grassmann variables, whenever you differentiate, it is theta 1 which will be contributing, but since the derivative is passing one Grassmann variable, it should pick up a minus sign. So these are the rules we have to keep in mind. And now we can discuss the Dirac Lagrangian. Our fields are of this kind. Immediately you know that if we write a Lagrangian, okay, so the field, their derivatives, all are Grassmann variables for us. So you can see that the Lagrangian will be linear on it. It cannot have a quadratic terms like, say, this. So they will not be in the Lagrangian, and also equation of motion will be first order in derivatives, and that's what is Dirac equation. If you okay, let me write it. So Dirac equation is first order in derivatives for each component. Okay, so let me write down the Dirac field, Lagrangian matrix field. The action will be written as, we need always, because in a complex quantities, both the real parts are free. So either you write it always in the real thing, for example, each you break them in real and imaginary part, or you treat this and its complex conjugate as independent variable. But uh, I am not, I am taking something else as independent variable. We will see what it is. So there are two independent variables, and the action you can write as psi bar x. So this is the Lagrangian density. So immediately you can see, if you vary psi bar, so this will lead to this quantity, and in the action there is no psi bar mu. It does, you can see that Lagrangian does not have any derivatives in psi bar. So uh, zero, and therefore the Euler-Lagrange equation will be this, which is Dirac equation. But you also need to vary psi, and for doing that, that you will be keeping in mind that they are Grassmann variables. So let me take this derivative, and psi in the Lagrangian we treat psi and its derivatives independent. So del L del psi will be the contribution will be coming from and eventually it will be minus minus plus, because it's a Grassmann variables, times this will contribute to 1. So differentiation with respect to Grassmann variables, you have to take care of a sign. So this, if you pay attention to this, but you can see that psi has derivatives in the Lagrangian. So if you compute the momenta, keeping track of Grassmann variable derivatives, you can find it. And you can write down an equation of motion, which is nothing but okay. So in a sense, we have got two equations, one governing psi bar, another governing psi. But we know that we only want one equation, that is the Dirac equation. Therefore, we need to make some identifications, and the identification you can check that the identification should be psi bar gamma mu. That will lead the equation on psi bar to be nothing but complex conjugate of Dirac equation. You have the Dirac equation, take complex conjugate, you will get the equation in psi bar if you identify this way. Okay, so this is important. I will give two more reasons. One, why this identification should be there. First of all, they are complex. If we do not identify, then there are four independent variables matrix variables. Each component has two. Better there are some identifications, but the identification is like that. But I will give two more reason for this particular identification. Another is the reality of action. Action should be real valued. And because of the gamma matrices, like in the Lagrangian, they have the gamma matrices. It is not very straightforward if you take just a dragger and you will find it back. It is actually not. And so when you take L dragger, you can actually find mu psi. In doing so, I have assumed psi bar is this, then it will lead to this relation, and you will see that action is invariant, action is same, because total derivative terms does not matter. Also, here you will see that you have to use a chain rule, but that is with respect to space-time derivatives. For example, here you can write this quantity, you can write this gamma mu psi plus psi bar gamma mu del mu psi without costing any minus, because it is space-time derivatives, not with respect to Grassmann variables. So yeah. Okay, so this total derivative term will go away, and it will finally give the same action. So in a sense, is dagger equals to S, which makes it real. And the third reason will be clear later from the Lorentz invariance, but for that we need some machinery to develop, and then I should take some questions. But okay, I might have missed some mu nu. I don't know. Like I am now not keeping track of it, but you can correct it. Whoever has these questions, that there is a index error in the eta matrix, but you can correct it. It's there in the note. Yeah. So I will now be discussing the Lorentz covariance of Dirac equation. Okay. So what transformation property should we assign to Dirac field under Lorentz transformation, such that the Dirac equation is Lorentz covariant? We want the same physics in any Lorentz frame. So what are Lorentz transformations? These are transformations of this form, which we need to transform these matrices, but how? So we'll proceed assuming that there is a matrix which depends on the Lorentz transformation parameter. So infinitesimally, this is identity plus omega. Omega mu nu is the small parameters. So this will enter in L. L is a 4x4 matrix that mixes the components of psi. But at this stage, we don't know. But we will be requiring that the Dirac equation is Lorentz invariant. So let's and see that how the for that requirement, if we can deduce the property, transformation property of the field. Okay, so psi x is, I am bringing everything in terms of del x prime, that's the m. So this is L inverse psi prime x prime, so that I will use. And this depends on some continuous parameters, but which are space-time independent. So this will pass through the derivatives. So you can bring it to this form. Okay, let me do it. And this, this is just the lambda matrix. So I am writing a prime because this is now with respect to del x prime. So you can pull lambda inverse out and write things inside. And this will be and these are numbers. So because these are metrics when you write as a lambda, but when I am meaning mu and nu, they are the matrix component. So there's a so the Lorentz transformation matrix, they are the elements of that matrix. So only matrices here are the gamma matrices and the L and its inverse. So you can bring that together, number you can pass through, and this will be this. So you see that this should be equals to gamma mu. Then it would be we will get back the Dirac equation. So if it is valid in one system, say suppose you require it to be valid in this system, this reference frame, and the other one is nothing but L times, okay, so this will tell you that Dirac equation is nothing but Dirac equation in the other untransformed frame. So if it is valid in one frame, in the other frame it will also be 0. So okay, meantime we got the required property on our representation matrix L. What is the property? This is gamma mu nu L, gamma nu L inverse should be equals to gamma mu, and this is important property, and that should determine what these gamma matrix are. And one can multiply this relation by L inverse A and L from both sides, and these are the numbers, so this will directly hit here and also here. So you will get gamma mu nu. Gamma nu is L inverse gamma mu L. So they are equivalent. Okay. So we can do further. We can take infinitesimal transformations, which are these. And we know that gamma mu nu is minus gamma mu nu. These parameters should follow these relations. This is the properties of Lorentz transformations. And L of lambda, we can expand around 0. So this is an infinitesimal version of omega around 0. And you can plug this in the relation and you can find this. These are arbitrary Lorentz transformation, arbitrarily small quantities. So what we should equate? We should equate the antisymmetric part on both sides. By definition, I have taken S. This we'll call it spin matrices. These are antisymmetric in rho sigma indices, because if since it multiplies omega, better we should define it with the only having antisymmetric matrices. That will only matter to us. And however, this side, the antisymmetric part is half of antisymmetrization of that. So this is what should contribute is rho mu gamma sigma minus antisymmetric in rho sigma. So eta sigma mu gamma rho. Okay, so we'll get eventually it will lead to so the transformation generators, the spin generators, will see that in the spin representations, we will call it, so L lambda forms a representation of Lorentz group. We'll soon, it better be, because it transforms the, it transforms the psi. So we'll call it a spin representation, and the generators satisfy a particular relation in terms of gamma matrices. Gamma matrices properties are known to us, and now the S matrices. And I will give an exercise that the solution is, because they depends on gamma matrix, and you can check that using the properties of gamma matrix that they solve the above equation. So this is the solution. You can explicitly check, and you can also check that with this identification, the S mu nu matrices satisfy the matrices satisfy Lorentz algebra. Which is so some product of eta and m. Okay, so you can plug m equals to S mu nu and check that this relation. So this is the Lorentz algebra, and this should be satisfied. So I should maybe take some questions at this point, and then I should proceed.
There are some questions in the chat as well.
Okay. Okay, so why do we choose? So that's a definition. And that's how Grassmann variables are, they works. So we'll just, these are called Grassmann numbers. A generic element in the, in these variables are the functions I have written. So these are the functions in Grassmann variables. And you can see that suppose this term is there, the same term can be written as minus theta 2, theta 1. The same term can be written as. And if you differentiate with respect to del del theta 2, you should recover minus C1 to theta 1. But if you differentiate with respect to this, you may recover this. But there is an ambiguity. To fix it, we have defined that always you have to first take it on the left, right? Like the arrange the term so that the variable is on the left, so that already there is a minus sign, and then differentiate. Okay, so that's by definition. And I have, yeah, so omega is antisymmetric. What's the, I did not get the question. Could you please explain S? Okay. So we are, although it's mostly I will discuss what S is, we'll see very concretely what S are soon. But let me tell that psi transforms as the, there is a half. It is customary to avoid like double counting because they are the antisymmetric. So in 4x4 antisymmetric matrix, there are 6 independent components and it multiplies with this. So the independent component would be this. So they are 3 and they are also 3 because ij antisymmetry is there. So essentially S1, 2, is 2, 3, is 3, 1. So these are the independent you can take. They are matrices. It is because they act on psi. When you take infinite simile, this is identity minus I by 2 is mu nu psi x. So this should be matrices. And we have seen that they are nothing but the 4x4 matrices in terms of, can be written in terms of gamma matrices. So, and also they satisfy the Lorentz algebra, and it should be because we are expecting psi to transform in a representation of the Lorentz group. And if you know what is the Lorentz algebra, like angular momentum algebra, you may know. For example, the angular momentum algebra is Ji Jk, or say J is I epsilon I jk. So these are the angular momentum algebra that generates rotations, or SU2 algebra. But okay, so rotations are included in the Lorentz algebra. So you will see, and you can also check that the rotations are nothing but I think with a half is jk. So these will be rotations, and they actually satisfy a angular momentum algebra. I will probably, if time permits, I will come to this point later. But and that's what so there will be also boost. So in the Lorentz algebra, you can write it, there are 6 independent m mu nu. In our case, m mu nu is s mu nu, and some of them are 3D rotations, some of them are the Lorentz boost that mix x and t. You know, the Lorentz transformation mixes the position and the time. So the boost will be nothing but, okay, whenever I write this algebra, I by definition I define it as lower. It's just a fashion, nothing else. So this should be the generator of boost, whereas this will give the 3D rotations. And we will see that the representation we have taken, and you know that this angular momentum algebra has some spin representation. We will see that we will and have a spin half representation. Okay, so any more questions? Okay, I will allow. Yes, please.
Sir, sir, on page number 4.
Sorry, which page?
Page number 4.
4, okay. Yeah.
So in the down, I gamma 0 dou 0, is that plus sign or minus sign for three components? For three space components.
This is plus sign.
The both are plus signs. I mean time component and space components.
Yeah, it's both plus sign. That's why you can combine it as this. So it's as a Einstein sum. You can think of gamma 0. Yeah.
So that's why we have changed the notation for complex conjugates, I think, because gamma 0 complex conjugate is gamma 0, but gamma I complex conjugate is minus gamma I.
Yeah.
So that's why I think we have changed the notation, yes.
Well, here if you keep track
No,
of,
sir. I'm not talking about here, then after.
I have defined here, it is with pi upper, not lower. In actually, if I do it properly, one should start with this. So this one should start with. If you and then you see that we know that pi goes to I del del t, but p upper I goes to I del del t. So yeah, this should solve. I have checked that this should solve this. Finally, one should arrive with a plus sign.
Yeah, okay.
Yeah.
Thank you.
Okay, one more question and then, yeah. Hi. L dagger equals to L inverse. No, I have not used L dagger equals to L inverse. I have just given an L, the Lagrangian. I have computed what is L dagger, because and saw that it's actually not even equals to L. So the computation is here, and the Lagrangian is also given here. So the Lagrangian density, you can, since they are matrices, gamma are matrices, you can take dagger and you can compute, and you can find that it is L minus total derivative, which does not matter for the action. Yeah. Yes. okay, if there is no question, I will proceed further, and then we will take a break for 5 minutes. Today I have to cover a few more things, and it's the last day, so I think you will not mind. So we want to compute the dagger of S. You can compute using the, because S has been written in terms of gamma matrices, and we know that gamma I dagger is gamma I, gamma 0 dagger is gamma 0. And you can show that few of the generators are anti-Hermitian, and those related to the rotation generators are Hermitian. And this will make the representation non-unitary, because in the sum you have both the generators, and L lambda is not unitary. You know that if you write a matrix e to the power IA, any matrix B dagger B should be identity, that is the property, and B dagger is minus I A dagger, and if it is the generators are Hermitian, then this leads to identity. So L dagger is not L inverse. Oh, by L you mean, okay, sorry, maybe in the question you have mean by L you did not mean the like not Lagrangian, but the representation matrix L that acts on the spin. Yes, it is not unitary. It's actually non-unitary. And that's what we got. We have Dirac equation. We wrote a action for it. We wanted to check, even you don't need to write an action, just the covariance of the Dirac equation under Lorentz transformation. You have to assign some property on the field, the transformation property, and they transform in a non-unitary representations, and that's related to Lorentz group. Lorentz group, it does not admit a finite dimensional unitary representation. So all unitary representations should be infinite dimensional. So that's from group theory. But I will not go into that now. But yes, they are not unitary. So yeah. Okay. So next, from the relation we have obtained for the which we have solved. Well, we do not, but it is an exercise for you. Using this, you can check that gamma 0 commutes with Sij, whereas this anti-commutes with A0i. That you can check. And using this, you can also show that psi bar goes as psi bar x L inverse. So I will sketch a proof, but just let me tell what it means. It means that psi bar psi is the Lorentz invariant quantity, because they goes as L inverse psi equals to psi bar x psi x. And the Lagrangian should be, Dirac Lagrangian should be Lorentz invariant. And one of the term, the mass term, is Lorentz invariant. And other term also, that will be an exercise, but I will just sketch this property. And this justifies why we need to define psi bar with multiplication by gamma 0. So this will justify that. So that is the third justification I talked about. Now I will sketch how you can see this. And so psi bar x is psi x dagger, and this goes under Lorentz transformations. This, so every quantity I am taking, it's Lorentz transformed one, and this is, you know, psi x dagger 0, and L lambda gamma 0 is, I will prove for infinitesimal Lorentz transformations for small omega. And we know that, so I have written down this quantity. We know that these are not Hermitian. If it would have been Hermitian, the psi, if, okay, if L was unitary, so S was Hermitian, so L inverse equals to L dagger. In that case, psi dagger psi would be Lorentz invariant. It is because this should go to psi dagger L dagger and L psi, but L dagger L for unitary representation, it is identity. But this is not the case, and we need really a gamma to make it Lorentz invariant. And that's the third justification. So you can plug this in the relation here to see how it transform. And okay, so here I have written, so omega mu nu is mu nu dagger. I am not bothering about factors. It is something like that. The summation convention is implicit, and we know that this is minus, but they are Hermitian, Sij. Now, the property I have just mentioned, that gamma 0 commutes with Sij, however, anti-commutes with S0i. So, since we have a multiplication by gamma 0, when you pass through towards the left, this gamma 0, you will see that gamma 0 will go as and from the from commutation and anti-commutation, it will make this minus to a plus, whereas it will leave the other term unchanged. So you can see that this is mu nu, S mu nu now, because I have used the dagger already here to make it related to the without dagger terms. Okay, so using this, you can actually show L lambda dagger gamma 0 is at least infinitesimally we have shown that this is identity plus I by 2 omega mu nu s mu nu. So earlier there was, to start with, there was a minus, but we have a plus, and also this dagger has gone away. So it is without the dagger, because you have taken the gamma 0 towards the left, and you can identify these as the infinitesimal version of L inverse, because L inverse is e to the power plus I by 2 omega mu nu times S mu nu. So the sign changes. I should write it here. It is e to the power minus I by 2 omega mu nu. So L inverse really should be okay. Okay, so I will now solve for Dirac equation, and then we'll take a break. Okay, solution. Again, I will only sketch the important points. We'll try plane wave. Okay, so you can see the Dirac equation leads to Klein-Gordon equation. If you multiply it by this, you can see that therefore plane waves are solution, you know, but we are not multiplying. We will not take this route. We will not take this route. So what we will be doing is we will try a plane wave solution, which is kx, and k is some k0 and k, and we don't know what k0 is. We'll see what it is. So if you plug this, you will immediately find I this. So it should satisfy this, and for no, and this is a matrix. As psi is a matrix, F also should be a matrix, so everything works. And for we don't want it to be invertible. Why? It is because then only solution is F equals to 0. We don't want. So we want it to be non-invertible. It means that this operator, okay, I have, yeah, so this I should not be there, because if you, when you use del mu on e to the power I k dot x, there is I k, and yeah, sorry, there is it's minus I k mu, so there is minus, yeah, we have taken with minus I k mu, so it's minus I k, and there is I, so in front of that, so it will lead to k mu, and there is gamma mu outside, so it will lead to k slash. Yeah, so this matrix, the determinant should be 0, but it is hard at this stage to compute the determinant with the proper well, it will take some effort using the properties of gamma matrix. I will take a shortcut route. So what is that? Just for the sake of argument, like I will just argue now. So we have this, we are multiplying by this. Immediately this will make it, since we know the gamma nu equals to 2 eta mu nu identity, the anti-commutator of gamma mu satisfies this relation, and it would lead to this, and this is a number. Therefore, we are multiplying this. It's a matrix multiplication, so I should write maybe a dot. Yeah, so you see that there is positive and negative energy, and that's why the wave function interpretation will not go to that. We will be dealing with something called the positive root of it, which is omega. But we will keep both the solutions, but always we will express things in terms of omega. But thing is that to get this equation, we have in a sense squared. We have multiplied by something. So are both of them valid solution? This both the sign that we have to justify. Why I am saying that? Suppose you have a equation x equals to 1. You know the solution is 1, but you square by hand, and you demand that your solution is plus minus 1, which is not true, because originally your equation was only linear, and that was the case. So are both of them actually solved Dirac equation or not? Like are they satisfy this condition? It turns out that both of them actually satisfy, but I will just argue. So actually we are solving this equation what we squared, but we will now not do the squaring, but we will go to a rest frame of the particle where it will just look this, because the momentum is 0, and there the equation, it is just for the sake of argument, and it is the shortest route I can take for now. So gamma 0 is a matrix. It will act on fk. It will be m by k0 and f of k, and we know that gamma 0 has two eigenvalues, because gamma 0 square was identity, and gamma eigenvalues was plus minus 1. So immediately we know that m by k0 should be, because this is an eigen equation for the gamma 0 matrix, we can identify as a eigen equation, and there are solution which is in the rest mass frame. It's just plus minus m. So indeed Dirac equation what we are supposed to solve has two solutions, but they are 4 by 1 matrices fk, and therefore there should be 4 independent vectors, so each value will be doubly degenerate. So 2 independent eigenvectors for each eigenvalue. So since they are 4 by 4 matrices, so I should write it that each eigenvalue. Now I am not in the rest frame anymore. That was just to argue. You can actually take a longer route. I am just here for arguing. So I hope it is clear. So each eigenvalue, this with the plus sign or minus sign, leads to 2 independent eigen vectors. Okay, so the solutions are fk will be some us k. Now I am, since k0 is related to k vector, I am writing everything as only function of k vector minus ikx, and there could be another solution which is some vs k e to the power plus ikx, s equals to 1 and 2, because each eigenvalue. So this corresponds to the positive one, this corresponds to the negative one. But so what we started with? We started with in the solution, we started with some f k times e to the power I k x. If you break it, it will be I k0 t or x0 plus k dot x. So whenever this is negative, so it suppose we plug minus omega k comes with always the positive square root. It would become I k0 t0 plus k dot x. However, in a fashion I have written here, so this is okay. This means that okay, I should write what k is here. K I am allowed only with the plus, but I am taking two solutions. This should be the negative one. But let me check what are the exponentials. The first exponential is nothing but omega k t plus k dot x, and the second one is I omega k t minus, okay, I have an I k dot x. So actually the negative solution you can find, we have just got, it should be with plus, but you can call whatever is momentum, you can define a negative of that. That's what we are actually doing here. You could have called Vs as a minus k, but that's even in the Klein-Gordon theory you can do that. But omega k is same as omega minus k. So we with this understanding we will only use k. So finally, if something is function of minus k, we can call it some v tilde and identify it with as some function of k. So it does not matter. So we will be taking a linear combination of these. And anyway, our integrals have d3k, which runs over positive and negative. So both the part will have positive and negative. So it will not be a problem. But what comes with a minus sign here, what comes with a plus sign here will lead to creation and annihilation operators. So the coefficient of them will lead to creation and annihilation operators, because finally the commutation with the Hamiltonian turns out to be that should be the deciding element. And we'll plug this in Dirac equation, the two type of solutions. Okay, so now if it is confusing, let's try this and plug in the both of them in the first one we have already seen, plugging in the Dirac equation. This one we should try to plug in the Dirac equation. You will get these relations. US k equals to 0, and this should be plus. It is because of the reason that either you can directly plug and see, because e to the power I k x gamma mu del mu will be with a minus ik, and in Dirac equation there was a minus m. Together it will give you a okay, so I should write this because it is I square is negative, so it is gamma mu k mu, and in Dirac equation there was a minus. So yeah, so you will get actually yeah, that way you can also motivate that you try both of them. But important thing is that you have for each of them, because the first one, and you stick to k0 to be plus omega k only, but you try two types of solution, I k0x and I plus K0x. So this immediately, since K0 is positive, this leads to the negative one. And finally, you have both the solutions. But psi is not anymore a wave function. So we will not have, we will see that we will not have the problem of negative energy, although we need to use something more, need to impose something more for that. So, okay, sorry, this is not US, this is VS. Yeah. So these are the, okay, that was VS. VS has, VS comes with the plus sign. So we are trying this. Yeah. So let me write down the properties. And there are some 4x4 matrices. One can define, one can choose a normalizations, because Dirac equation was only sensitive to this. You can have a some k dependent constant, say C of k, and you can still solve the Dirac equation. So the normalization property we will be taking. That's always we are doing, so that finally the commutation relations are, so this is R and some S, both RS run over 1 and 2. Yes, so V and U, U R dagger, okay. Okay, so I will motivate this. So you can see that we have normalized. So different RS, like for the same, so you were what? You were the positive energy solutions. Omega k appears. And in the V, in the exponential, what appears is minus omega k. So they are doubly degenerate, and there are two of them, and there are also two of them. Each of them are normalized, like the eigenvectors you have taken orthonormal basis. So that's why this delta RS. But whenever R equals to S, they contributes. That's contributes to unity, but not unity, fancy factor I have taken. And similarly for V dagger V as well, U dagger U and V dagger V, but the cross ones, because they are for among the different eigenvalues, we can see that they are always orthonormal. But again, that is the one that k is related to minus k. So you have to assign that properly. For what is k, vector k for V is actually minus k for US. So these type of normalizations you have to use, and I will just write down a spin sum, and that will you can take it as exercise. And to test this, you need to use this normalization. So with these normalizations, only you can find this. The way you can test this, you can. So what are the bases? The basis is UR and VR, or I can say VS. So some numbers. So these are the, okay, this is U and VS. So these are the bases. So you can add this relation on the basis and see that both sides behave similarly. They give the same number. And if an operator uh, acts on the basis element in a same way, so you can have the equality. So that way you can test this spin sum, but you have to use this normalization. So they are really specific to these normalizations. So I should take a break at this stage for 5 minutes, and you can ask. I am here. You can stop the recording, but I for a break. But I am here to, if anybody has questions, I can answer. So we can take a break for 5 minutes. Yeah. We'll not be using much this stuff like this U and V, just to mention the property I have stated. In the notes, you can find more details. You should work out them. Yeah. So any question? Yeah, let me know if you have any questions. Otherwise, we can take a break for 5 minutes, and we'll start in 5 minutes. Yeah. Okay, so we will be quantize these fields, and we'll see that there are fermions and antifermions. They will have some charge which is positive for the electron and negative for the positron, the particle and antiparticle. And we will also see the propagator for them. We will also see the Weeks theorem for them. That's my plan, because this will be used by, I think, Taushik. So it will be important. Yes. Well, I have also given a reference, so far what I have discussed is in Peskin. I will also I have also consulted the other book by P.B. Pal and Lahiri. So Yeah, but mostly is the third chapter of Peskin. Yeah, so far I have stated S as spin, the small s or r. I have stated that the spin sums, so it's runs. I have motivated that there are two independent vectors, call it u1 and u2, similarly v1 and v2. So spin is suggestive. We have seen that we have found out what our transformation matrices which acts on the Dirac field. We know that this actually the generators also we have found, which is gamma nu, but we have not seen that they are really the spin half representation. We need to really compute the J3 and see that what are the J3 eigenvalues. So J3 is defined as ijk is jk, and these are known. Gamma matrices are given, but I have not stated any explicit representation of gamma matrices. I will, if time permits, I will give a representation of gamma matrices, which is wild representation. But the question is, if you know gamma as a 4x4 matrices, you can compute S and you can compute J3. What are the eigenvalues of J3? It will turn out that they have eigenvalue plus minus half. Each of them are doubly degenerate. So that will, one way to see spin is that. But I have not stated that so far. So it's a suggestive name. We are calling it spin. Fermion will be clear soon because we will be using anti-commutator, so it will lead to Fermi-Dirac statistics. But still, it is spin half or not. It will be the root should be one root should be that, but there are many other ways to see that these are actually spin half representation of Lorentz group. One should denote by a half as well. Okay, how can we know which one are the Grassmann numbers or not? Okay, so we actually the canonical quantization what I am doing, Grassmann numbers are not needed, but truly the field action what is written, if you do not treat them as Grassmann variables, you cannot actually do the path integral. I mean, that will not be the correct path integral quantizations, where you will be summing over all fields, taking a exponential weighted with action. But for canonical quantization, you can do it by hand instead of imposing commutators. When we promote the coefficients a dagger as operators, we will at end see that you need to impose anti-commutation relations, and that should instead of commutation you have to lead anti-commutations. So that will actually take care of, you don't need Grassmann numbers, but I introduce them so that it's always tailor-made, that our fields, for example, these U and US, they are if you US you interchange, they will pick up a sign. They should pick up a sign because you have to you have to take a sign out of it, or well, not US, because they are matrices. The coefficients in front of them will promote them as operators. We'll see them that promote them as operators, and suppose B are coming with VS, and we'll see that you should the using Grassmann variables, it makes it tailor-made, that it's natural that when you interchange there is a minus sign, but it's not needed. Historically, did Dirac himself start with his equation or by physical? I don't know, but the books like in relativistic quantum mechanics, when you do, you try to see it as wave equation. Then the procedure initially I described, that you make the square root by introducing Dirac gamma matrices. And that's the root. I don't know whether that's the, probably that's the root Dirac took. That's why they are called Dirac matrices. And yeah, so that's the physical motivation. You can say that you need to do the square root and to obtain the Dirac equation. Well, for relativistic quantum mechanics, you can look at Bjorken and Drill. That's a standard reference. I also like that a lot. That's probably the advanced quantum mechanics book, or I forgot which volume. I haven't read that book, Grainer. I haven't read. So I also forgot whether Sakurai has it. So, okay, I am giving one reference, that is Bjorken and Drill. To they have all the steps basically to know about Dirac equations. Yeah. Okay. So at this stage, I should start, and I will. My plan is to take 20 minutes, but I can go slightly over it because I want to show you the full quantization, sketching many things. So just, I mean, thank you for your patience. So the Fourier decompositions we'll be taking as yep. So this is the Fourier decomposition. So you now know what is these two factors are. But I have introduced the coefficients. I have called one AS, another one CSK. But I have identified CSK with some metrics, because at end you will see that whatever comes with the plus sign here in the exponential, the coefficients in front of them will have the appropriate property with the Hamiltonian to call it a creation operator. So since you will see it at end, I am not writing it with some CS and then identify it at end as call it some creation operator. To start with, I am doing that, but you at this stage they are not operators, they are matrices. And okay, well, I think I should write it star, but soon we'll promote them at as operators. So call it BS dagger, because they are really numbers. The matrix components are already in US and VS. So because psi is a matrix and they should be the numbers, I should have called them star, and then when we promote them as operator, we should take it. But we'll take them as Grassmann variable. So whenever there are products of them, whenever we pass them, interchange them, that will pick up a sign. You can also write psi bar. So that is Dirac equation. You can compute this. This minus is coming from the Grassmann. And in the Hamiltonian formulation, and the density is given by if you plug everything, you will get important thing is that the time dependent part go away. Okay, another thing is that I have usually, okay, in when they are not Grassmann numbers, they are ordinary variables. This is same. But I have to decide a factor, so it can be written actually minus, and that's what for, we are doing classical field theory so far. Consider them as star, no dagger, okay? So we are doing classical field theory so far. So there is an ambiguity for classical field theory of Grassmann variables that you can probably look for some online references. It's always customary to write it psi star with psi dot with phi pi, or in terms of minus you can write it minus like the if you switch you have a minus sign here. So and okay, so here from the Lagrangian the phi dot term go away, only the what remains is the derivative with respect to position. Okay, and then you can use the normalization relations. You can plug the mode expansions, the Fourier decompositions, and finally you will find H equals to this. You have to do the x integral. So you mode expand, plug what is psi and psi bar. You plug, actually you just need to plug psi bar also you need to plug, and then you do the x integral. The k integral will be outside, and you can do this using the representation of gamma matrix, delta functions. You can x1 minus x2. Okay, so I will be doing the x integral, so it will be 8 to the power plus minus I. Yeah, it is because you have to plug representation for psi and also psi bar. Here you call it the variable k. Here you call say k1 and k2. Finally, you have to do one k integral as well. Finally, whatever is left, say k1, I am calling it k. So that's the final relation. In order to, and we will promote everything as operators. Now A star, B star. This will now go to operators. And you can see that if you allow a anti-commutation relation. Otherwise, there is a negative energy for the modes. See, for real field, we have identified B to be complex conjugate of S dagger, but that we are not doing here because we are not even real. It's complex field, so they are independent. And we have seen they are coming from two independent solutions. They are not related. And also psi was complex field, so they are not related. So now you see that you have two types of particle, but we'll explain it in a minute. But if you switch it, so first let me write D3K omega K sum over S, AS dagger AS with the same K. Okay, so now if you just use commutation relations, make it this, apart from having an infinite energy that we can remove by saying that we are interested in the energy differences. But if you just so our fields are anti-commuting, and this AS should have those and BS should have those property. They are the anti-commuting variables. So whenever you switch, it should pick up a sign and it will make it a plus. And then we will get D3K omega K sum over S this. Okay, so the commutation relations we will be imposing are ARK, AS dagger K, delta RS. The spin should be same. There is a K prime, and show equals to BRK, BS dagger K prime. So this is the anti-commutation relation, I should say. And all others vanish. AA, BB, AB, AB dagger. Between AB, everything vanishes, and even between AA and BB also the anti-commutations vanishes. AA dagger and BB dagger are non-vanishing one. And using this, you can plug it here, and you will still get the divergences from the delta functions, which we will be removing by hand, or we'll always use the normal ordered prescription. So normal ordered prescriptions are these, and AS dagger will be this, etc. And also for B. So normal ordered Hamiltonian, the creation operator should be taken in the left, or the annihilation to the R, so that any operators, the normal ordered operators should have zero vacuum expectation value. So that's another way to remove the divergences, and we'll be doing that if you do not want to put so if you take a normal order H here, you'll see that it will make it already the negative one because of the property of the normal ordering. So in a sense, what we got, you can say that it is the normal ordered H. So that I am writing down, and that is our final formula. So it is already normal ordered. So that's the Hamiltonian we'll be using. And the anti-commutation relations I have given, I have imposed to quantize the system. You can say that earlier we are imposing quantization rules for the field and its conjugate momenta by Dirac prescription. But usually whenever you get mode expansion in write the Hamiltonian, looking at the Hamiltonian, you can impose commutation relation in the modes, and that's also a procedure of quantizing. But using the anti-commutation between A and B, you should be able to check this, the components of the equal time commutator of this is actually this, and this has pi, so pi psi b includes this, the dagger of this we have seen. So this is the anti-commutation relation you can find. So just the commutators, you are now dealing with anti-commutator, and it was needed for even to remove the negative energy solutions, and that's what most of the book will do. They will not use Grassmann variables, but at this stage they will prescribe. They will also get this because I mean, without even using Grassmann variable, you can reach to that, and then they impose the anti-commutation relations. And for us, because of their Grassmann variables, they are tailor made. That's what I wanted to say. I will also now define what is vacuum. You can see that it is annihilated by all the AK, and there are another type of particle, but one particle states are this. So these we will be calling fermion, and this as anti-fermion. Although now it is not clear that why I am calling fermion. Just we could have told that two kind of fermions. We'll now see that it has the Fermi-Dirac statistics, but still calling it particle and antiparticle will be clear when I will define the charge. So for now, you can see that A is dagger K, A is dagger K is 0 because of the anti-commutation property. Similarly, B R dagger K, B R dagger K. So they are 0. So you cannot excite a single state many times. So A S K square lead to 0. So these kind of states will not be possible. So each of them are both the particles are first of all, both of them are eigenstate of energy. I should say I will okay, I should have said that, but okay. I mean, I have not written it in my notes, but yeah. So you can check that each of any of the state will pick up the state back. You can plug either this kind of state or with the BS. So both are one particle states with energy k square, square root of k square plus m square. Their energy eigenstates, and they satisfy Fermi-Dirac statistics because a single two particles on the two particles or two antiparticles with same spin and same momentum cannot be created. So that's the Fermi-Dirac statistics. Now I will talk about E1 charge and why I am calling it particle and anti-particle. So the Lagrangian has a symmetry under psi goes to q theta psi x. Q is a given number. It will be the charge, a fixed number, because at this stage we don't know whether they are electron, positron, or some other spin-up particles. So just and actually Dirac Dirac spinners, all are any massive spinners are can be represented by these Lagrangian. Only spin half is required. Any spin half particle, massive spin half particle can be the Lagrangian can be written in this form, and theta is a continuous real parameter. So it is a continuous symmetry. In Q you can call it, say Q equals to, you can take electron charge, no matter, but theta is the continuous parameters, and psi bar goes to e to the power I q theta psi bar x. You can actually check they are related, and infinitesimally the field changes minus I q theta psi and delta theta psi bar I q theta psi bar at each x. And this is a symmetry of the Lagrangian. I am not showing it, but it will give you a Noether current, which is you can compute from the formula I have given earlier. Basically, the space-time part, because this is not space-time transformation, this will be 0. Only the change in field you need to take, that was earlier I called as delta theta, that will only be non-zero, and basically this will be nothing but delta theta phi del theta, which will be minus iq psi x, and you can find the Noether current. It turns out that the Noether current is this, and the Noether charge, which will be conserved, the conserved charge, which is Q, will be J0 integral over the spatial direction, and you can see that this will be d3x. And what is J0? J0 is psi bar gamma 0 psi, but psi bar is psi dagger gamma 0, and gamma 0 square is identity. So it is q d3x psi dagger psi. So that will be the charge, and you can plug the mode expansion, take the normal ordering, and normal ordered q will be given as this. Therefore, you can see that the A modes, particles created by A dagger, has the positive charge. The others contribute with a negative charge, and that's why we are calling it a U1 charge. Why U1? Because this type of symmetry, e to the power iq theta, they belongs to U1 group. So all theta is continuous parameters. They are element of unitary 1 by 1 matrix, and that's why it is called U1. So this U1 charge, the charge related to U1, particle and antiparticle, is actually contributing in a opposite way. So that's why we will be calling it fermion and antifermion. And normal ordering is taken, it is because so it is always will be taken so that the vacuum has 0 charge and 0, so n of h and n of q will lead to that vacuum has 0 charge and 0 energy. So these are the assumed property of the vacuum. That's why we'll always talk about normal ordered. You can check this. Okay. Okay, so we have discussed what is particle and anti-particle. Now I will be the last section of the lecture. I will take around 7 to 8 minutes, I hope so. And I will be discussing the Green's functions and Wick's theorem. Or okay, allow me 10 minutes. So the Green's functions, which will be eventually the Feynman propagator. Earlier we started with Feynman propagator and showed that it satisfies it is the Green's function of the Klein-Gordon operator, but we'll take the other approach because of time constraint. So that is the 4x4 identity matrices, and this minus I has been taken out because we know that at end what will be identified as the Feynman propagator is this SF. S stands for spin. You can, I don't know, it's probably stands for spin, but they are 4x4 matrices, and because there is gamma matrices which are 4x4 matrices. So what we'll do, we'll plug Fourier expansions of all the quantities above. So it is d4k sf tilde k e to the power minus I k x1 x2, and delta function Fourier transformation is also known to us, delta 4. This is d4k. If you plug this, and the differential operator will act directly on the exponential, eventually what you are going to have is k minus f S tilde, the Fourier transform of the 2-point function. We are yet to see that this is a 2-point function of the theory. And this turns out that, okay, there is a minus I on the left-hand side. On right-hand side, it would read as I. And immediately, you can multiply it by our usual trick. You will get an operator, but this side now it is a number. Therefore, SF tilde k is k slash plus m divided by a number. Okay, so this is the Green's function, but it suffers some problem. For example, we have to integrate it over k. So k0 integral will it is along the real axis in the complex k0 plane, and it has pole at plus minus omega. I should say omega k square minus m square, k vector square minus m square. So it has poles. So you cannot integrate it. If you integrate, it is in the integrand is 1/0 at some point. So it will be diverging. So there are many ways Green's functions are defined for any differential operator. We will take the Feynman's prescription. We will replace m square to m square minus I epsilon. And finally, we will take, therefore, here it would come with a plus sign. We will take at end after integrating, we will take epsilon tends to 0 plus. So that and why Feynman prescription is important? You can define other Green's functions, and the operator has many other Green's functions which are retarded and forward Green's function. But this one with this prescription will lead to the time ordered product of 2-point function, which I will state in a minute. But let me write what is the so it is this by k square minus m square plus I epsilon. Many people also write it as k slash minus m plus I epsilon some prime. But it is, yeah, basically m square minus I epsilon. You have to square root to get this, what is epsilon prime, which will be related to, I think, epsilon by 2m. I think, check it. Okay. Okay, so some epsilon prime, where epsilon prime tends to 0. So many people will write this, but it is something in the denominator there are matrices. So whenever people write this, it is understood that they mean this. It is just for notational simplicity. People will write this, but with this choice of I epsilon, so this is a matrix because the gamma matrices in the numerator are matrices. So they have alpha beta element. One can check that if you Fourier transform, do the contour integration, K0 contour integration like the previous day, it will give you psi alpha x1, psi beta x2 acting on 0. So this is the time ordered product of psi bar. So that's the Feynman propagator. And again, it's actually tailor-made for Grassmannian, but let me, because in the book, they might not use the Grassmann variables for canonical quantization. So to relate with them, whenever x1 0 is greater than x2 0, and this would be x2, the time ordering means this, whenever x20 is greater than x10, but with a minus sign because of the anti-commutation property. I will now state one, so that is what time ordering means. I will now state what is the general correlator will look like. Alpha 1 at some x1, then alpha n at some xn, some fields, and then you will also some conjugate fields, I mean psi bar fields. Okay, call them beta 1. We could have started with alpha n plus 1 located at x n plus 1, but call for simplicity, notational simplicity, now call it say some beta m ym, and take the vacuum expectation value. So this is a general correlator will look like. It is non-vanishing unless n equals to m. Sorry, it is vanishing. What's the English? Yeah, so they vanishes unless n equals to m. So yeah, that should be the correct wording. So whenever there are same number of psi fields and same number of psi bar fields, only when that is non-zero. That's what I mean. And that is actually a consequence of charge conservations, because so immediately what it will lead? It will lead that it is psi alpha 1 x1, psi alpha 2 x2. This will be 0 because there is, both of them are psi fields, no psi bar fields. And then also it will lead to psi alpha bar x1, psi alpha okay, alpha beta say call it beta 1, beta 2, x2, that's also vanishes because there is, both of them are psi bar field. So it means that only non-vanishing components are with psi, equal number of psi and psi bar. For example, for 2-point function psi and one psi and one psi bar. So it's actually one will like vacuum has 0 charge, and then acting something, if you okay, psi and psi bar has both A and A dagger, right? So either they can create a particle or annihilate a antiparticle, like that. So the net charge in the vacuum will be 0. Like if you create a particle, you also have to create a antiparticle because out of vacuum you can only act them. So the propagator has consequence from this charge conservation. I'll state what is Wick's theorem, and Wick's theorem applies to free fermions, true. With the usual, now you have there will be a difference in a sign, that a sign must be included in front of each term according to the number of anti-commutations required to bring the contracted fields next to each other. So let me give an example rather than stating it I am not writing down the statement. You can find it in my notes. And suppose these, and you know that in the time ordered product will be normal ordered product of all the combinations, but only when psi and psi bar is there, that is not vanishing. Psi contraction will be vanishing. So, and I am already now computed within correlator. So this will finally lead to SF alpha 1 beta 1 x1 minus x3 times, so I am contracting these two, and the other two all should be contracted finally in the correlator. So it will be product of 2-point functions. Sorry, it would be alpha 2 beta 2 x2 minus x4 plus, but there are only two terms because alpha 1 alpha 2 contraction will give you 0. So minus x2 SF alpha 2 beta 1 x2 minus x3. But since to get this arrangement, the first contraction, you need to bring the psi field towards the left, it will pick a minus sign. Here for the last thing, you have to do this manipulation. Psi alpha 2x, psi beta 1 x3, psi bar beta 2 x4, but psi alpha x1 will bring this to in front, next to each other, and then psi alpha 2 x2, psi bar beta 1 x3, but this is comes with a plus sign because you have to change twice. Yeah. So this is the version of Wick's theorem. And finally, the last probably page of the lecture, I will state a representation of the gamma matrices. This is known as Wild representation. All the representations are unitarily equivalent for the gamma matrices. Basically, the spin statement, what I will show you now, under unitary transformations, the the eigenvalues does not change. So it will, I'll show that it is spin up particles. So it will remain. So while representation for the gamma matrices, this is some 2 by 2 0, and then identity 2 by 2 0, and then again identity. But gamma i's are given as 0, 2 by 2, sigma I minus sigma I 0. Sigma I are the Pauli matrices. One can show that these satisfy the anti-commutation property of the gamma matrices. By the way, I should say that that is called Clifford algebra. So this they will satisfy this. One can compute the S mu nu. It turns out that all the S mu nu are block diagonal, 2 by 2 block diagonal. So they are actually, so the representation lambda L, which contains this S mu nu in the exponential, it's actually it's a reducible representation of the Lorentz group. But okay, so let me state what it is. So it is sigma I 0 minus sigma I 0 and sigma let me write, okay, let me write all of them. Sigma S23 will be half sigma 1 0 0 sigma 2. So these are all 2 by 2 matrices. So finally it is a 4 by 4 matrices, and S 3 by 3 1 will be half sigma 2 2 by 2 and sigma 2. Okay, so great. The angular momentum which is related to these are the angular momentum, and in particular J3 you can check it is epsilon 312 S12 plus epsilon 321 S21. I have stated only the S12, but it should be, because the antisymmetry property, it should be with negative 2 S21, that you can compute everything from here and check that whether they are it's satisfied or not. And finally it will give half of sigma 3 0. So you can see the two copies of Pauli matrices, and the eigenvalues of these J3 as a 4 by 4 matrix, the eigenvalues are plus minus half, each have two vectors. So doubly degenerate, because it is a 4 by 4 matrix, so it will eventually lead you, so spin up down for each particle, so all total 4, so it will eventually lead 2 spin up particles. Okay, so I should stop here, and thanks for your patience, and I can take questions. Yeah.
Thanks, Bhaiya. Should I stop the recording?
Yeah, you can. Yeah.